All right, we're starting lesson 3.5 with a classic problem. It stopped. The boat sank. Okay. Anyways, we have 40 feet of fence to enclose a rectangular garden alongside of the barn. What is the maximum area that you can enclose? All right, so they gave us this picture here, a barn. We have 40 feet of fencing to cover this fence. We don't need fencing along the barn because it's going to be bordered by the barn. So we're calling each kind of like width, I guess, of your barn X. So I'm just going to call the length Y for now. You can use L if you want. So what we're trying to maximize, so I call this my primary equation, is our area. We know we can find the area of this rectangle by just doing length times width, or X times Y. All right. What we need to do is find another equation, which I kind of call, like, sometimes I say secondary, or like our helper equation, to put this area in terms of just one variable. Okay, so this is where the 40 feet of fence comes into play. We know we can find the perimeter of this rectangle, which that would be my fencing border, by doing 2 lengths of the width, which is X, plus 1 length of Y. Again, we don't need 1 by the barn. We know we have 40 feet of fencing, so I can plug that in for my perimeter. All right, now here's where we're going to do a little substitution. I can decide if I want to put my area just in terms of X or Y, but which variable is easier to solve here? Definitely Y. And I usually, because I'm so used to working with X's and like equations, I usually put it in X anyways. Okay, so we're going to substitute that in here. And I can write my area in terms of X, or like as a function of X. That's what that notation would mean. Would be X times 40 minus 2X. I'm going to go ahead and distribute that X through. And then you can see here we end up with a quadratic polynomial equation. So I mentioned before that you solve these in pre-calculus by finding like the vertex, which is really, in this case, this is like a stat face parabola, it's a U down. So the vertex would be our max. And now we're going to use calculus to solve this. All right. So how we locate maxes and mins in calculus is we start by finding critical points and where there's horizontal tangents or when the derivative is 0. So let's go ahead and take the derivative of this area function, a prime of X. And it's also easier to do if you write it not as a product, so I don't have to use any special rules. We can just do 40 minus 4x. So I start with looking for my critical point, so that's when my derivative is 0. And at any points where my derivative is undefined, but this is a nice polynomial, we don't have to worry about that. All right, so we get 10 as a critical point. Now, technically we're trying to find like the absolute maximum area, the absolute max. So really what we should do is use like that candidates test. This was like way back in the first lesson of chapter 3 that we did, where you plug in your critical points and you plug in your endpoints on the interval to figure out where is your highest point on the whole entire graph. But since we're talking application problems, a lot of these, they are close intervals kind of, but if you're thinking like the possible numbers here that X could be, or like our domain, I mean, technically X could be 0. We would just have a, one line of 40 feet. But X couldn't be any more than 20 either. So if you were to test like this closed interval, like using the candidates test, I'll just show you quick. You plug in 0, you plug in your critical points. You don't really have to do this, but you plug in 20. And then if you plug in these to your area, this one would give you an area of 0. This one gives you an area of 0. And this one gives you an area of 200. So like obviously that's like your highest, your max. So I just want to like preface this where like sometimes it can occur when we have like a closed interval at one of the endpoints. But for the most part, like you just have to think of like what makes sense in terms of your application problem. Like I don't really have a closed interval here. Like you could say like the open interval, it could be anything in between 0 and 20. And in that case, like we wouldn't use candidates test to determine which one's the highest because we're not including endpoints. All right, but what you do have to show is I know I have a critical point here, we have to show it's a max. So we can do that two ways. We can do the first derivative test or the second derivative test. That shows me relative extrema, right? So it's a good review for our quiz too. So the first derivative test is when you do a number line. Now, again, I really shouldn't have arrows here because it's not like we can go to negative infinity. You could cap it if you wanted to, 0 and 20. All right, so then you would test points in the derivative to the left of 10, to the right of 10, and you'll get positive and negative. So it's increasing and then decreasing. And since this is my only critical point, I do know that that would be my max in like that interval from 0 to 20, that open interval, 0 to 20. You could do first derivative test. What your textbook more commonly does is a second derivative test. And that to me depends on like if your derivative is a nice function and you can easily find the second derivative. Sometimes the second derivative test is quicker. Remember that also locates extrema. Let's review over that one quick. Second derivative test. Second derivative test, you find the second derivative, which in this case it would just be -4. Okay. So we don't need to make a science chart for this one. Okay, I'm not locating points of inflection or anything like that. I'm trying to figure out if this is a max or min. Well, obviously my second derivative is always negative no matter what I plug in for x. So obviously if I plug in 10 here, I'm still going to get out -4. So what that means is that my function is always concave down at every point, which makes sense because we know this is a parabola. So we could also say that, oh, it's a max because we know it's a critical point. And at that point, the second derivative is negative, so it's concave down. So that's used to find extrema using the second derivative test, find extrema with the first derivative test. Now, we didn't actually answer the question because they want to know what the maximum area is, and we just found what the x value would be. So you could figure out what y is, yada, yada, or you could just use, we have our area function right here. We could just plug 10 in. I actually did it right here. You could just plug 10 in. And we get 200 feet squared for our maximum area. Max area when x is 10. Okay, so that's basically what we're going to do in 3.7. So I'm just going to talk through that again if that was confusing. And we're going to do, obviously, a lot of problems. But basically, you're going to find your primary equation, the one you're trying to maximize, or sometimes it's minimized, depending on the application problem. And sometimes it's a little like geometry formula. Sometimes there's a couple like revenue and cost ones where we're like given the equations. And then our second goal is we have to find like another equation that kind of relates the two variables. This is where it kind of reminds me of like related rates. Write the primary equation in terms of just x or in one variable. And then we're going to find maxes and mins using calculus, which means we'll always find our critical point. And then we can either use the second derivative test if it's easy to do that. Like, ooh, we have a nice easy polynomial. Let's find the second derivative. Plug that in. Oh, it's concave up, so that has to be min. okay? Or you can do a first derivative test for them as well. Like I said, your textbook more commonly did second derivative test. Now, keep in mind, we're actually locating like absolute extrema, like what is the maximum, like the highest point. But when we have these context problems, a lot of the endpoints like don't make sense. So we don't really essentially need to do like the candidates test. Okay. So that's all this lesson is, and we're just basically going to do like a bunch of problems. So let's just kind of go through the next slide here. This is just normal. Okay. So here's some like keywords that are really like indicating to you that we are trying to find relative extrema. It might not say the word maximum in it. The last problem did. What is the maximum area? It could say something like this. What is the size of the most profitable production run? Most profitable, that's a maximization in disguise. What is the least expensive shape? That's a minimization problem in disguise. What is the stiffest rectangular beam we can cut from a 12-inch log? So to optimize, actually, you guys do these problems in algebra too. I just taught them that. Remember when you used to have to like shade a bunch of inequalities and like look at the shaded region where they overlapped and then find like the vertices and then like plug them in to figure out which one was the max and the min? Kind of remember doing that? You were doing optimization problems. You were trying to find the maximum or minimum of the possible points in the feasible region. So basically now we're going to tie it to calculus. We're going to find the greatest or smallest value that we can use to model whatever application we're doing. And as I mentioned before, all optimization problems, this is the way I like to think about it, are absolute extrema problems, kind of just like in disguise. Okay. So basically, we're going to be doing all this calculus that we've been doing in chapter 3 of finding these critical points, determining are these maxes, are these mins, what makes sense in terms of this application problem. So do I need to test like other points? We're doing like all that calculus just like in word problems. Or as I like to say, math in real life. Some of them, like just looking through, find two numbers. Oh my gosh, you guys do these in algebra too. You just do it by like finding the vertex. Okay, so now it's just using calculus to locate that instead. This one's like find two numbers whose sum is 20 and whose product is a maximum. So that has the maximum product or the highest product. What's the largest area this rectangle can have? Kind of like our classic problem. We do a minimize one. What production level would maximize our profits? Good stuff. Okay. I don't think we'll have time to try one today. I'm just going to talk through the steps on the next slide, and then that way when we pick it up on tomorrow we can actually go through some of these problems. Okay, good. So here's kind of like your textbook copy and pasted the step-by-step for doing these optimization problems or like applied minimum maximum problems. That's what optimization is. Identify all given quantities and what we want to be determined. If you need to, make a sketch. Write a primary equation. So that's the one that you want to actually maximize or minimize. So if you're looking for the largest product of two numbers, your product is your primary equation. If you're looking for the largest area of a field, area is your primary equation. Reduce the primary equation in just one variable, and you might have to use a little helper equation or secondary equation that also relates to the variables of the primary equation. So like in the last example, we used the perimeter to help us rewrite the primary equation in terms of just x. Determine the feasible domain, that is, determine the values for which the stated application problem makes sense, kind of like we did 0 to 20. And then determine the desired max or min by using calculus techniques. Okay, so you're going to, we could either use first or second derivative test to check if they're maxes or mins. Because sometimes, guys, critical points doesn't always mean is max or min, right? We've looked at some examples like that. If it is a closed interval, we should technically use the candidates test, so you should like check the endpoints too. That really does not come up a whole lot, but just something I need to be clear about. Okay, that's all we'll do in those notes for today, and we'll finish them up tomorrow, or at least get most of them. Oh, perfect. We'll plan on quizzing Friday.